Hello everyone and welcome to our calculus notes for 7.7. Today we're talking about indeterminate forms and L'Hopital's rule. So that's pretty cool. Anyway, let's talk about indeterminate forms, just a little bit of recall. So if we're trying to find the limit as x approaches -1 of 2x squared minus 2 over x plus 1, we'll remember that we had something called direct substitution that we could use to solve this. So in other words, we're just going to take that -1 and substitute it in for x, and then see what comes out. Okay, so just plug this in here. And let's see, -1 squared is 1 times 2, 2 minus 2 is 0. And then -1 plus 1, we get 0 right here. So direct substitution fails in finding the limit because this is an indeterminate form. Now, if we look at the graph of 2x squared minus 2 over x plus 1, we can see graphically what's happening as we're approaching -1. Okay, whoa, and right there we get an undefined. Okay, so to the right it's defined, and then right there at -1 it's undefined. So we actually have a hole in our graph here, and you can see that because of the x plus 1 in the denominator, we expected that at -1. Okay, but looking at this, what is the limit? Well, it looks like the limit is at -4, because that's what this function is approaching. Now before, when we had the limit of a rational expression that gave us an indeterminate form, we would have to solve it using long division. Okay, so we would just set up x plus 1 into 2x squared minus 2. So x goes into 2x squared, 2x times, and then we multiply. 2x times x gives us 2x squared, 2x times 1 gives us plus 2x, and then we have to subtract, and we get 0 here, minus 2x minus 2, and we can just keep going. So x goes into -2x, -2 times, and now we multiply -2 times x, so we get -2x, and then -2 times 1, and we get -2, and when we subtract this, we actually change our signs here, and we're left with 0. Okay, so we know now that we could find the limit as x approaches -1 of 2x minus 2. Okay, and here if we use direct substitution, now it's going to work out. And we do get -4, which is what we had seen graphically. So take a look at a couple of indeterminate forms that you might come across. And we're going to take a look at all of these today. We got 0 over 0, any form of infinity over infinity, 0 times infinity, 1 raised to the power of infinity, 0 raised to the power of 0, and infinity minus infinity. So these are the indeterminate forms to look for here. Now it brings us to L'Hopital's rule. It says if the limit as x approaches c, so some number, of f of x over g of x, so a rational expression there, produces an indeterminate form, then that limit is going to equal the limit as x approaches c of f prime of x over g prime of x. And this is what's known as L'Hopital's rule, and a lot of times we'll just put an LH over the equal sign showing that is what's happening. So the limit of your rational expression, which would yield an indeterminate form, equals the limit of the derivative of the numerator over the derivative of the denominator. So it's important that you take the derivative of each one, that we're not actually using the quotient rule here. So if we did want to take a look at our first example there, the limit as x approaches -1 of 2x squared minus 2 over x plus 1. We've already shown that we get the indeterminate form 0 over 0. So let's go ahead and apply L'Hopital's rule. So it's going to be the limit as x approaches negative 1 of the derivative of 2x squared minus 2, which is just 4x, over the derivative of x plus 1, which is just 1. Now we can use direct substitution, and we get 4 times negative 1, which equals negative 4. And you can see that it's the same answer that we got using long division. Alright, so let's take a look at a couple other examples. Now anytime you do these problems, don't just jump into L'Hopital's rule, because it's not going to work if we don't get the indeterminate form. So we need to verify that the limit as x approaches 0 of e to the 2x minus 1 over x yields an indeterminate form by direct substitution. I usually just do that down here. We'll plug in 0. So we get e to the 2 times 0 minus 1 over 0. Well, this right here yields e to the 0 power, which is 1. And so we have 1 minus 1, which is 0. So we do get 0, 0, our indeterminate form. Okay, that means we can use L'Hopital's rule. We've got our LH right there. And so this is going to transform into the limit as x approaches 0. Okay, we need to find the derivative of the numerator. So the derivative of e to the 2x minus 1, well, derivative of e is just e. And then don't forget your chain rule, so times the derivative of 2x, which is 2. And then the derivative of x is just 1. So therefore, we can just use direct substitution now. So we're going to get 2e to the 2 times 0. Okay, and again, e to the 2 times 0 is e to the 0, which is 1. So this is 2 times 1, which is 2. So there is your limit. All right, let's try another example. So we have the limit as x approaches infinity of ln x over x. Okay, so let's use direct substitution here. So we'd have the natural log of infinity over infinity. Now, if you'll recall the natural log function, something like this, and this keeps increasing without bound. So the natural log of infinity is going to also go to infinity. And on the bottom, since it was just x, infinity over infinity, so this right here is your indeterminate form. Alright, that means we can use L'Hopital's rule. So we got our LH right there. So we want to transform this, the limit as x approaches infinity. Well, the derivative of natural log of x is 1 over x. The derivative of x is 1. Sometimes you might want to clean up these fractions. It's not too difficult to see in this case, but this would just be the same as 1 over x. And now if we use direct substitution, we would get 1 over infinity. So if we have a constant over a really, really, really big number, that's the same thing as saying 0. Now, in our next example, we're going to see that sometimes you have to apply L'Hopital's rule more than once. So here we have the limit as x approaches negative infinity of x squared divided by e to the negative x power. So first, let's go ahead and show that this produces an indeterminate form. So direct substitution, we would get negative infinity squared over e to the negative of negative infinity. Okay, and if we look at this, negative infinity squared, well, still gives us infinity. And then the negative times the negative would make that positive. So e to the infinity, that's also increasing without bound. So we get infinity over infinity. So there's our indeterminate form. which means let's go ahead and use L'Hopital's rule. Alright, so this equals the limit as x approaches negative infinity. Well, the derivative of x squared is 2x. And the derivative of e to the negative x is e to the negative x. And don't forget the chain rule. So the derivative of negative x is negative 1. Alright, and now let's go ahead and try to use direct substitution. And I'm just going to put it down below here. Okay, so using direct substitution, we get 2 times negative infinity over negative e to the negative infinity. So 2 times negative infinity is still just negative infinity. And then e to the, well, that would be infinity, and the negative gives us negative infinity. And so this is another one of our indeterminate forms. So what that means is we're going to go ahead and have to do L'Hopital's rule a second time. Okay, so it's going to be the limit as x approaches negative infinity. So that doesn't change. Now we take the derivative of the top, which is 2, and the derivative of the bottom, which is going to be, let's see, e to the negative x, but then the negative times the negative just makes it positive. Alright, and now let's go ahead and use direct substitution here. So we have 2 over e to the negative infinity. And we already said that this e to the infinity is going to be infinity. And 2 is just 2. And 2 over a really, really large number just equals 0. So there we go, our limit is 0. Alright, we're going to take another look here. The limit as x approaches infinity of e to the negative x times the square root of x. Okay, so let's go ahead and try direct substitution as is. We will get e to the negative infinity times the square root of infinity. And if we look at e to the negative infinity, okay, we're going to have to remember what the e function looks like. And it just looks like this here. So as x approaches negative infinity, e is approaching 0 right there. So this does give me 0 times, well, the square root of infinity is still just infinity. So 0 times infinity, there is our indeterminate form. Now we may not see this function as being a rational function, which is what L'Hopital's rule works for. So in this case, we're actually going to flip this negative exponent so that we get the limit as x approaches infinity of the square root of x over e to the x. And now we can see we have our rational function that we can use L'Hopital's rule for. Okay, so the derivative of the square root of x, well, remember the square root of x is just x to the 1/2. So if we're finding its derivative, that's going to be 1/2 x to the, let's see, 1/2 minus 1, so negative 1/2, which is 1 over 2 root x. Okay, so it's been a while since we did that. So we're left with the limit as x approaches infinity of 1 over 2 root x divided by e to the x. Now when you get a fraction divided by another number, what you want to do is just multiply these two together. So this is really going to equal the limit as x approaches infinity of 1 over 2 root x e to the x. And now let's use direct substitution here. So we're going to get 1 over 2 root infinity times e to infinity. And notice in this case, all this, that's just expanding continually, so it's 1 over infinity, which we know is 0. Alright, so before we do direct substitution, just make sure that we clean this up a little bit. It's going to make finding that limit a little bit easier, especially when we're going to infinity. All right, let's move on. All right, in our next example, we have the limit as x approaches infinity of the quantity 1 plus 1 over x raised to the x power. So let's go ahead and try direct substitution. We would get 1 plus 1 over infinity raised to infinity. We already said that 1 over infinity is 0, so this is 1 to the infinite power, okay, which was one of our indeterminate forms. Okay, so that's indeterminate, meaning let's go ahead and try to use L'Hopital's rule. Notice we don't have a rational expression. Same type of problem as the last one. And looking at this, there's no real simple way to do that. So what we're going to do is a little bit of side work before we actually can apply L'Hopital's rule. So let's just set this up as an equation. Y equals the limit as x approaches infinity of 1 plus 1 over x to the x power. Now in doing this, we are assuming that the limit does exist and that it equals y. So that's why we do that step. Now, what's problematic for us here is that we have a power of x. That's what's creating our indeterminate form right there. So we do have a method for getting that x out of the exponent. So the trick is we're going to take the natural log of both sides. Okay, what we're left with here now is the natural log of y equals, well, when we were looking at the limit, that's just going to pull to the outside, and then the natural log will go to the inside here. So we have the limit as x approaches infinity of the natural log of 1 plus 1 over x to the x power. And now, using our laws of logs, we can take that x and put it out in front. So we get the natural log of y equals the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. Now, right here, we can check and see, did that solve our problem? So if we used direct substitution, we would get infinity times the natural log of 1 plus 1 over infinity. Okay, and we know this equals 0, and the natural log of 1 also equals 0. So we have infinity times 0, and if we recall, this also is an indeterminate form. So we're still not quite there. So looking at this function right here, we know it gives us an indeterminate form with the limit, but it's not a rational expression. So therefore, we can't use L'Hopital's rule yet. What we want to do is rewrite this so that it is a rational expression. So I'm just going to say equals the limit as x goes to infinity of the natural log of 1 plus 1 over x divided by. Okay, now what can I divide by so that it's the same as multiplying by x? Well, if I divide by the reciprocal. Okay, so this is the trick. When you have x times something, you can get it to be in a rational expression by dividing by the reciprocal 1 over x. And now we can use L'Hopital's rule. Okay, so all we got to do is take the derivative of the top and the derivative of the bottom. So we just need to recall the derivative for natural log. So the derivative with respect to x of the natural log of u is 1 over u du. Okay, so we're going to let all of this stuff equal u here. So it becomes 1 over 1 plus 1 over x, and then times the derivative of 1 over x, which is going to be negative 1 over x squared. Okay, if you want to see that derivative with respect to x of 1 over x, remember we could change this to being x to the negative 1, and then if we use the power rule, we get negative 1 times x to the negative 2, and then if we just brought that back under, we get negative 1 over our x squared, which we can see right here. Okay, so there is the derivative of the numerator. And now let's go ahead and find the derivative of the denominator. Oh, the derivative of 1 over x. How nice, we just found that. That's negative 1 over x squared. Now what's really great about this is we have a common factor there that we can cross out. So we're really just left with this. And again, we'll recall that this is the limit as x approaches infinity. Okay, so let's just clean this up a bit. This is going to equal the limit as x approaches infinity of 1 over 1 plus 1 over x. And now let's use direct substitution here. So we're going to get 1 over 1 plus 1 over infinity, which we know is 0. So we get 1 over 1, which equals 1. Now, what equals 1? Is that our final answer? Well, if we look way back over here, remember we're looking for this limit, but we had to say that this equaled some value y. And so we went over here, and then we had to take the natural log of both sides. So what we're really finding here all along is the natural log of y. And then you can see as we progressed across, all of this still equals the natural log of y. So when we get down here to 1, we have to recall that the natural log of y equals 1. Okay, so we have the natural log of y is equal to 1 here. So very important, when you use that natural log technique, you have to come back and do this one final step. And so what we're going to do here to solve for y, which remember is the limit that we're looking for, is we're just going to raise both sides by e, because e to the natural log, those are inverses. And so this is going to leave me with y equals e to the first power, or just e. Okay, and y again was that limit, so there's e. Now, what's interesting about this is that e is a constant. E is a constant, it's just a real number. And so if we can take a look at this function right here, this function, as it approaches infinity, is going to equal that constant of e. So what we've just accomplished here is just as exciting as saying that pi equals the circumference over the diameter of a circle. Okay, so pi is that, and we know that e, the number e, equals the limit as x approaches infinity of the function 1 plus 1 over x to the power of x. Wow, that's pretty impressive stuff. Nice job finding the value of e. All right, we're going to move on, take a look at some other indeterminate forms that we can come across. So here, this is a one-sided limit. It's sine of x to the x power. The limit as x approaches 0 from the positive. So if we do try direct substitution, we're going to get sine of 0 to the 0 power. And we know sine of 0 equals 0, so this is 0 to the 0, and that's our indeterminate form right there. Okay, so you'll recall, just as in the other problem, we have this raised to the power of x, and that creates a problem for us. So we're going to follow the same type of process. We're going to say that this does equal some value y, and we're going to say that y equals the limit as x approaches 0 from the right of sine x to the x. We're going to use the same procedure as before, so we're going to take the natural log of both sides. So we have the natural log of y equals our limit as x approaches 0 from the positive of the natural log of sine x. And we can go ahead and take that x power and we'll just put it out in front first, save ourselves a step there. Okay, now because we transformed this function, we do want to make sure that we still get an indeterminate form. So this would be 0 times the natural log of sine 0. Okay, now sine 0 is 0, so this is 0 times the natural log of 0. And if you recall, the natural log function, again, looks something like this. And so the natural log, as it approaches 0, goes to negative infinity. So here we have 0 times negative infinity, and this is an indeterminate form right here. So that means we have to keep going, and it does mean we could use L'Hopital's rule. But we have to remember the little trick that we did with our x value. So we're going to rewrite this as the limit as x approaches 0 from the positive, and this will be the natural log of sine x. And what did we do with that x value? We divided by 1 over x. And that's important because now we can use L'Hopital's rule. Alright, so the derivative of natural log is going to be 1 over u times the derivative of u, which is cosine. And then this is going to be divided by the derivative of 1 over x, which we know as negative 1 over x squared. And I always get so excited to apply L'Hopital's rule that oftentimes I forget that this is still the limit as x approaches 0 from the positive. So make sure you still get that limit in there. Now we can go ahead and clean this up a little bit. So it equals the limit as x approaches 0 from the positive. Well, this would be 1 over sine times cosine, which is really just cosine over sine, which is cotangent, which is still divided by negative 1 over x squared. And now we're going to use the same trick that we did with the x and the 1 over x, except now we're going to go backwards. So if it was times x, it's divided by 1 over x. So if we have divided by negative 1 over x squared, it's going to become, now let's get the limit in there, it's going to become times negative x squared times cotangent x. Okay, now before we can use direct substitution, and let's bring our work back over. So here we have the limit as x approaches 0 from the right of negative x squared, and then cotangent x is 1 over tangent. So I'm just going to go divided by tangent x. Okay, so cotangent x equals 1 over tangent. So we can just divide it there. So let's try direct substitution now. We're going to get negative 0 squared over tan of 0. And so we get 0 divided by, well, tangent of 0 also equals 0. Boy, so we got another indeterminate form. So L'Hopital's rule is just not being kind to us right now. But since we still have a rational expression, let's go ahead and try to use it again. Okay, we're going to get lucky one of these times. So we have the limit as x approaches 0 from the positive. Well, derivative of negative x squared is negative 2x. The derivative of tangent is secant squared. Alright, before we can use direct substitution, let's go ahead and change this so we can use our calculators to find it. Okay, so we still have negative 2x. And secant squared is going to be the same as 1 over, well, secant is 1 over cosine. And then if it's squared, we know we can just rewrite it just like this. And so now let's go ahead and try to use direct substitution. So we get negative 2 times 0 over 1 over cosine of 0 squared. All right, so the numerator is easy. That's just 0. Cosine of 0 equals 1. So this is 1 over 1 squared, which is just 1. And 0 over 1 is not an indeterminate form, and that just equals 0. Okay, now after all that, it's going to be very easy to forget what that 0 is equal to. And we have to go all the way back to the beginning and say that 0 is equal to the natural log of y. Because remember, we changed that. Okay, so we'll just come down here. All right, the natural log of y equals 0. And we're going to solve that by taking e to the power of both sides. And we're going to be left with y equals e to the 0 power, which is 1. Okay, so what this means is the limit as x approaches 0 from the right side of sine x to the x power equals 1. And there is our final answer. All right, let's move on and try one final example. Okay, the limit as x approaches 1 from the right side of 1 over ln x minus 1 over x minus 1. So again, we need to try direct substitution. So we get 1 over natural log of 1 minus 1 over 1 minus 1. And natural log of 1 is... I'm just going to put a little note here that this is approaching from the right-hand side. So it never actually is going to equal 1. It's just as we're getting to 1 from the right-hand side. Now we know the natural log of 1 does equal 0, so we might think this is 1 over 0. And then 1 minus 1 is also 0, so we get 1 over 0. But if we think as what is the natural log approaching to as we get to 1, okay, again, if we look at this here, if we are approaching from this side, notice we're getting closer and closer to 0, so this number is actually getting smaller and smaller right here. So if we let this number get smaller and smaller and smaller, shrink down, the 1 over a really, really small number is going to equal infinity. And the same thing's happening right here as well. 1 minus 1, as we're approaching from the right-hand side, notice this is getting very, very, very small. So 1 over a really small number is also infinity. Okay, so this is the indeterminate form infinity minus infinity. Okay, so that means we could use L'Hopital's rule if it were a rational expression. So to be able to do that, we're going to have to figure out this minus sign and turn this into one fraction. Okay, so we're going to do that with common denominators here. So you can see ln x, so we're going to multiply the right side by ln x over ln x. And then we also have a factor x minus 1. So we're going to multiply the left by x minus 1 over x minus 1. So we have our limit as x approaches 1 from the positive of x minus 1 minus natural log of x over our two factors, x minus 1 and natural log of x. Okay, since we already determined that there was an indeterminate form, we can use L'Hopital's rule. So the derivative of the numerator, well, derivative of x is just 1, and then minus 1, that's 0, and then minus the derivative of natural log of x, which is 1 over x, and then divided by, well, it looks like we have a product here, so we're going to use the product rule. So it's going to be our first function, x minus 1 times the derivative of the second, so derivative of natural log 1 over x, and then plus our second function, natural log of x times the derivative of the first, which is just 1. Ha! And what did I forget to do again? Maybe me forgetting so many times is going to help you remember it. So it's the limit as x goes to 1 from the positive. As long as we remember at some point, right? Okay, now we do have this rational expression, and we may want to clean it up just a little bit. I don't really like this 1 over x in here. It's going to make it a little bit harder to find. So I'm actually going to multiply here by x over x, and we'll just distribute here and here. So we get the limit as x approaches 1 from the right hand side of x minus, well, 1 over x times x is just 1, and then divided by x minus 1 times, well, 1 over x times x is just 1, and then plus x times the natural log of x. Now let's go ahead and see substitution here. 1 minus 1 over 1 minus 1 times 1 plus 1 times the natural log of 1. Okay, that gives me 0 over, well, 1 minus 1, that's 0, plus natural log of 1 is 0. So we do have 0 over 0, another indeterminate form. Okay, so that means let's go ahead and use L'Hopital's rule again. Alright, so we need the derivative of the top, and we have the limit as x approaches 1 from the right hand side. Hey, we remember this time. So we have 1 over, well, the derivative of x minus 1 is just 1. And now we have another product rule of x times ln x. So it's my first function times the derivative of my second. So derivative of ln is 1 over x. And then plus my second function times the derivative of the first. So that's just times 1. And let's clean this up just a little bit more here. Alright, and let's just make some room right down here. Okay, so we have the limit as x approaches 1 from the right hand side of 1 over 1 plus, well, x times 1 over x is just 1, and then plus the natural log of x. So we get the limit as x approaches 1 from the right hand side of 1 over 2 plus the natural log of x. And now let's go ahead and try direct substitution. So we have 1 over 2 plus the natural log of 1. So here we have 1 over 2 plus 0, which equals 1/2. Now in this case, when we look back at our problem, we already had a rational expression from the beginning, and we didn't have to use that natural log thing. So this is just a straight equal sign for our limit all the way down to the end. So this limit equals 1/2. And that is your final answer right there. Alright, so that is indeterminate forms and L'Hopital's rule.